समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. A very happy new year and good morning to you. Can you see my slide and hear me? Okay. Thank you. Okay, so we will continue with the 1D theory, state of the art. We were introducing the kinematics in the previous class. We will conclude a few more aspects of the kinematics before getting into the overall picture of the 4 sets of variables and 3 sets of equations which govern the 1D problem, which is applicable to the wing as a whole, the fuselage as a whole, a helicopter, the entire length of the fuselage, or a particular tail rotor or main rotor blade. And also for the interior components like either the spar of the wing or the stringers of both the fuselage as well as the wing. So for all of these structures, this particular 1D theory will be valid. So that's why it's so significant in flight vehicle structures. Okay, so now we had looked at this schematic of the beam deformation, which is the primary source from which we get the kinematic equations. So to do that, we saw the undeformed configuration, what we showed in green over here. And then we also showed that the deformed configuration is eventually not a planar surface, but something which could be arbitrarily curved, and that is the blue surface that you see over here. And just for the convenience of introduction of variables, we introduced an intermediate configuration which we showed in pink or orange. That is basically a plane which is taken care of all the average deformations of the cross section, and the only thing missing is the warping, which is the difference between the blue surface and the pink plane. So we also said that this whole thing, this beam, that is, it could be the wing or it could be the helicopter rotor blade or the tail. This is deforming in a vehicle which itself is moving, and we said that the dynamics of that, namely the aircraft reference frame A, is got from the flight and space mechanics, if it's a space vehicle also, for example. And essentially all that we need to know is at a given instant of time, what is the velocity small v and the angular velocity small omega of that particular aircraft. If it's a helicopter, then it's a 2-step. One is from the rotor blade to the hub, and then from the hub to the helicopter frame. So the hub comes in between, because with respect to the helicopter, the rotor blades are rotating. So there's one more level involved over there, but otherwise it's pretty much the same. So we do not want the aircraft to be an inertial frame of reference. That's a very important thing, because in general, we might need to do this analysis when the aircraft is actually performing some maneuvers like a pull-up, for example, or some kind of a turn which could be banked. Whatever it is, we have to ensure that the accelerations are not something that are left out. So that's the reason why we don't require this frame A to be inertial. But most of the equations, governing equations of motion, whether you're coming from a Newtonian mechanics vector equations or from an Hamiltonian mechanics using the variational principles. In either of these cases, many of these equations are not valid when you do not have inertial frames of reference with respect to which you are having all these variables. So that's the reason why we also introduce an inertial frame of reference with respect to which this aircraft is moving, and we take into account this small v and small omega, which are the velocity and angular velocity of the aircraft. And so in other words, v can be varying with time because acceleration could be involved, and similarly whenever omega is non-zero, obviously there is an acceleration. Whenever there is a rotational motion, there is an acceleration involved. So essentially that's something that we are not assuming that the aircraft is an inertial frame of reference, which is unfortunately something that a lot of flexible body dynamics makes that assumption that it's with respect to the inertial frame, that is the aircraft is an inertial frame, which case the most stringent aspects, that is we saw in the flight envelope, the case where n is very large and the dynamic pressure is very large because of a large velocity, that is those corners of the Venn diagram are what are most critical. And so if you assume the aircraft to be an inertial frame of reference, you are actually leaving all of that out. So we are not doing that. So we are allowing for the acceleration, for the rotations, that's why the angular velocity is there, and for v to be small v to be a function of time as well. I'm repeatedly saying small v because we'll also be introducing a big V to refer to the velocity of the CG of that point of intersection of the reference cross section with the reference line. So that will be denoted by big V, and the angular velocity of the frame itself, that is the cross section, will be denoted by capital omega. So the capitals are reserved for that. That is why we are using the small for the aircraft. Now let's briefly summarize those equations that we had. One is we introduced a small b system, frame of reference b1, b2, b3, where b1 is tangential to the reference curve, and then b2 and b3 are tangent to the coordinate curves x2 and x3 at a particular location, which is the intersection of the reference cross section with the reference line. So reference cross section could be anywhere along x1 from 0 to L. Now, so all three, in other words, are tangential to the coordinate curves, but the coordinate curves themselves need not be straight. They could be curvilinear too if necessary. But in most cases, we do not require, especially x2 and x3, to be curvilinear. So usually they are straight lines. The x2 coordinate and the x3 coordinate run along straight lines. So typically you will have b2 and b3 still could be functions of x1 because of pre-twist. And that is a very common thing because of either washout or wash-in in the case of fixed wing aircraft, and because of the pre-twist in the case of the helicopter rotor blade. But if you're looking at probably a spar or something, unless the overall washout or wash-in is creating that kind of a pre-twist in the beam as well, you may or may not have it, especially in the stringers which are over a smaller location. Next, we also saw that the position vector of an arbitrary material point on the cross section is given by the position vector of the reference curve plus moving along the cross sectional space by x2 and x3 along b2 and b3 respectively. So b1, b2 and b3 are all in general functions of x1, but if it's a straight prismatic beam, untwisted to start with, then b1, b2, b3 are constant throughout the length of the beam. Next, we said that we are breaking up the overall motion into three parts. Two parts are rigid body-like motions of the cross-section, namely translation and rotation. The third one is for the cross-section also to have elastic deformations, and that means warping. And we said that warping is a three-dimensional field. It can be out-of-plane warping of the cross-section. In other words, it's no longer planar, and within the cross-section also it changes its size and shape. So, which is an example of which is the Poisson's effect. We saw that. And in general, this W field W1, W2, and W3 can be functions of all three spatial coordinates x1, x2, x3 apart from time. And then we also said that as far as the translation is concerned, we denoted it by small u, and the rotation by the direction cosine matrix Cij that we introduced. I also said you that there is no unique way of representing the rotation. Direction cosine matrix is one such way. We will also see the fact that we are introducing the curvatures of the reference line going from small r in the undeformed configuration to big R in the deformed configuration. There is a curvature that has happened, that is an elastic curvature over and beyond the initial curvatures that are there, which is because of the elastic twist and the elastic bending. So that could be an alternate way instead of the direction cosine matrix Cij to have that. So we will see the relationship between those two, because that forms the one of the fundamental equations of the kinematics, 1D kinematics. We have not yet seen that. We will see that today. So next is, we also mentioned that x1 may not map may not map directly. In other words, from 0 to L, each point along the undeformed configuration can move by different amounts along the reference curve, which is basically the new reference curve that R is created, and therefore we introduce this arc length S as a function of x1. So it could vary throughout the length. That's why S is a function of x1. Next, we also said in terms of the rotation, the small b1 has now become the big B1, but is no longer tangential to the reference curve. But there is also a possibility of a tangential system that you could introduce, especially if you want to compare with the Timoshenko beam theory, your results with the Timoshenko beam theory, just for validation purposes. Then you can introduce another coordinate system which is tangential. So in other words, instead of this big B1, B2, B3, you will introduce a big T1, T2, T3. We'll see that shortly. So when you do that, then you can explicitly introduce the transverse shear strains gamma 1 to gamma 1 3. Otherwise, there is no need to consider them. You will still get asymptotically correct results and very accurate results for all the three-dimensional fields. So whereas when you introduce the big B system, you will explicitly consider the transverse shear strains. So let's see what that means in terms of the position vector for the deformed configuration arbitrary material point. So this same material point, though in the figure it is shown to be on the periphery, that is on the perimeter of the cross section, it need not be there. It could be anywhere in the interior as well, and it could include the point at the reference curve also. So all points within the cross section are included over that. So that R hat, small r hat that you had, has now become big R hat. So the same material point, if you're trying to follow its contour, it has reached a new location. So in reality, it undergoes only three displacements, U1, big U1, big U2, big U3, but we are breaking it up into small parts. It is getting a joyride on this cross section through a translation, through a rotation, that is Cij brings small b system to the big B system, and then over and above that, the plane now becomes a surface because of the warping that is there. So these three parts that we are breaking it up into, because of which we need to introduce certain constraints. So I'll not go into the details of those things, because that's only essential for the derivation, not for the actual application of this end results. So we will not go into that. So but the way you apply the constraints will redefine these 1D variables and warping in different ways. For example, you can either consider the transverse shear strain to be a part of the warping, or it can be considered to be a part of the rotation of the cross section. So depending on that, the constraint that you choose would be different, or vice versa. This implies that, and that implies this in turn. So this big R hat, that is the position vector of the same arbitrary material point, which was at small r hat before deformation, now has come to big R hat from the same point in the that is, we called it as O, in the reference frame big A, So it has come to a new location, and that location is given by first locating the reference curve intersecting that reference cross section, namely this particular point. And so that point is given by the big R. Now that big R of x1 is different from the small r by just this u. So that translation that the reference curve points had, so small r plus small u is going to give you big R. But that's not all. To get to r hat, you have to move on the cross section also. But instead of moving by x2 and x3 along small b2, b3 like we did in the undeformed configuration, now we do it along the big B2 and big B3, which also in general are functions of x1. In the undeformed itself, it was a function of x1 because of pre-twist and the initial curvature. Now, over and above that pre-twist and initial curvature, you have the elastic twist and the elastic bending curvature, because of which B2 and B3 are also functions of x1, just like B1. Over and above that, we want to move from the pink plane that we see over here to the blue surface, because of which we are introducing these three warping measures, W1, W2 and W3, all 3D variables, in the sense that they are functions of all the three spatial coordinates. So now, next step, we introduce the 1D strains. So far we've been talking of the 1D displacements like U, and the 1D rotations which are contained within Cij. Why they are 1D displacement and 1D rotation? Because they are function of only x1 as a spatial variable, which means that they are one-dimensional variables. Now, in lieu of them, in lieu of U and C, we can introduce 1D variables, which are the extensional strain, the two transverse shear strains, which is not necessary actually to introduce explicitly the transverse shear strains, but we are doing it just to have some kind of a comparison with other existing theories in the literature, like the Timoshenko theory. Even without that, we can do it because we can include it in the warping. Now, the way we introduce that is through the derivatives of the position vector of the points on the reference curve, that is r prime. All primes refer to derivatives with respect to x1 taken in the A frame. See, whenever you have vectors, you take a derivative of them, you have to specify in which frame you're taking the derivative. On the other hand, when you're taking a derivative of a scalar quantity, like let's say pressure or temperature with respect to x1, let us say, then you do not need to mention with respect to which frame you're taking that derivative. But when you're taking the derivative of let's say a force or a displacement, which are vector quantities which have a direction, then you need to say with respect to which frame, because direction also matters there. So when we say r prime or any prime, any quantity is prime, we are referring to a derivative with respect to x1 in the frame A. So that is basically what we are saying, is that prime of any quantity is defined as dou by dou x1 of that quantity in the frame A. So this is the notation we use, a superscript A, or rather a prescript expressed in the top, to say that the derivative is with respect to that. So we will not explicitly mention that, because that is the default, and if it is with respect to some other frame, like the inertial reference frame, earth fixed, let us say, then we will explicitly mention that. I also mentioned that the earth fixed reference frame in reality is not an inertial reference frame, but for all practical engineering purposes, it's good enough to be treated as an in the time and space domain that we are interested in, it's good enough to be treated as an inertial reference frame approximately. So now we also say that we need the derivatives of the rotation. In essence, before going to the C prime derivatives, we want to introduce the derivatives of the unit vectors in the deformed configuration, namely B1, B2, B3, their derivatives. Now, as far as R prime is concerned, it has components along big B1, B2 and B3. The component along B1 is 1 plus gamma 1, 1. Suppose there was no deformation at all, you can see that you will not have gamma 1 1 and the gamma 1 alpha. So you will have all of them 0. So it would just become b1 plus just b1 alone. So in other words, r prime would have been b1, just like it was in this case. So here, this small b1 was by definition your small r prime. But in the case of the big R, its R prime is not equal to just B1 alone. If it were, then it would have been tangent. So that is what we will call as T1. That is, the vector T1 would be just that, it would just be tangential to a tangential unit vector to R, big R. So in other words, R prime itself is equal to T1. But instead of the T system, big T system, tangential system, we are introducing the big B system to explicitly bring out the transverse shear strains, which are these two quantities here, 2 gamma 1 alpha. And in all beam literature, when we talk about alpha or any Greek subscript, we are saying that it takes the values either 2 or 3. That is the cross-sectional coordinates, along the cross-sectional coordinates x2 and x3, the smaller dimensions compared to the x1 or the length dimension. So, and there is a repeated summation. So whenever there is alpha, which is repeated here that you see, it actually consists of 2 terms. That is 2 gamma 1 2 b2 plus 2 gamma 1 3 b3. So now, if the transverse shear strain was not there, all that would have happened is it would be tangential, but it would have had a stretch, because S is different from your x1, whether it has increased in length or decreased in length at different locations along the reference curve. That would be constituting this gamma 1 1. That is the extensional strain, which is a 1D variable. In other words, it's a function only of x1. It's not a function of x2 and x3. So it's basically how much the reference curve is stretching at different locations along x1 at different instants of time t. Now, so if you had introduced a T system, then just this first term would have been enough. That is 1 plus gamma 1 1 T1. So it is tangential, but it is no longer unit vector. It has undergone a stretch by this gamma 1 1. So which is why we are saying we are multiplying that unit vector T1 with 1 plus gamma 1 1 to get R prime. But now we are explicitly introducing the gamma 1 alpha, the transverse shear strains along the x2 and x3 directions of the cross section, as 2 gamma 1 alpha. They will be along the b2 and b3, and they contribute towards the R prime as well. So all of these actually is pure geometry. If you look at it, you don't even need to think of it as a beam or a structure, whatever. Just the if you go into the vector algebra of the 1D curves, then you can actually come up with these equations quite obviously. So this is something which is there in other literature as well, purely mathematical literature as well of curves. Then as far as the unit vectors are concerned, how they change with respect to x1 depends on how they are going along the bi. And this is again same way that we had talked about the small bi prime last time. We said that is equal to that's equal to small k cross bi. So any unit vector, when you want to see how it varies along a particular spatial direction, you have to an equivalent way of doing that. Instead of taking the derivative of that unit vector or any vector with respect to a particular reference frame, in this case A, you would instead just do a cross product with the curvature vector. Then you would get the equivalent thing. This is again a fallout of 1D geometry. So there are two ways of doing it. One is either taking the actual derivative, writing the expression for bi and taking the derivative, or just taking a cross product if you knew the curvature vector. So the same thing holds in the case of the deformed configuration as well. that your big BI prime is given now by the big K, which includes the initial twist, initial curvature, along with that the elastic twist and the elastic curvature. So that if you cross with the same vector whose prime that you want to take, if you're crossing it with that, you will instead get the prime. So this is an easier way of doing it if you knew the curvatures. So now we put these three together. That is what you had in the first equation of big R prime is equal to 1 plus gamma 1 1 plus 2 gamma 1 alpha B alpha. The two kinds of 1D strains we introduced there were the extensional strain gamma 1 1 and the two transverse shear strains, which were the gamma 1 2 and gamma 1 3. In engineering, we use the factor 2 to distinguish it from the tensorial shear strains. So now we can put all of them in a column matrix. So then we denote that by small gamma. The small gamma is a column matrix. So the small gamma that you see over here is a column matrix, and yes, I'll come to you, Subhashish. The column matrix, most of the column matrices that we'll be introducing here are 3 by 1. In the sense that because we are dealing with three-dimensional space and going to the one-dimensional configuration, so it will be 3 by 1. So this is all of that will be written in terms of column matrices like this. And column matrices are different from vectors. Vectors have a direction, whereas column matrices are just the elements of that vector along a specified reference unit vector system. In this case, the unit vector system is the big B system. So unless otherwise mentioned, it will always be the big B system. Only very few exceptional cases like this small k we will express in the small b system because it's basically initial twist and curvature. So for example, we will call small k without the underline. That is, if it is underlined, it's a vector. Now it's a column matrix, and then we would just call it small k1, small k2 and small k3, where k2 and k3 are the initial curvatures and k1 is the pre-twist per unit length. Yes, Subhashish.
Sir, got it.
Okay.
About this, yeah.
Fine. So then this gamma is gamma 1 1, 2 gamma 1 2 and 2 gamma 1 3. Next is from the second equation, we are introducing that big K. That big K is equal to the small k that we had over here. That is the initial whatever you had, column matrix, plus a kappa. Now that kappa is what we are showing over here as again a 3 by 1 matrix consisting of the elastic twist per unit length because of any torque that you are applying. That's a direct effect, but any other loading can also cause that because of the couplings. Then you also have the two bending curvatures, that is kappa 2 and kappa 3, about the x2 direction and about the x3 direction respectively. So again, could be caused by bending moments that you are applying about x2 and x3, but it could also be caused by other kinds of loads because of the couplings that could be there. Let me just clear all the pen markings. Oops. Okay. So then, yeah. Now, I mentioned that you could probably introduce a big T system, which is what I show over here, where you could have a T1 which is tangential to the reference curve instead of a B1 which was perpendicular to the reference cross section. So these are two alternatives, and one is more convenient than the other for different purposes. You use the big B system when you want to introduce the transverse shear strains explicitly and deal with 6 strain measures, 6 1D strain measures, gamma 1 1, gamma 1 2, gamma 1 3, kappa 1, kappa 2, kappa 3. But it's not even necessary to do that. You can get equally accurate results if you just use gamma 1 1, kappa 2 and kappa 3. To do that, you would instead use a T system, that is basically what you see over here, T1, and T2 and T3 are mutually orthogonal to that, but now they differ from the big B system by this angle that you see over here, that is 2 gamma 1 2 over there, right? So, and again in the other plane that is perpendicular to the plane of the book, you would have the 2 gamma 1 3 as well. So now this particular thing that you are introducing is what differentiates the big B system from the big T system. So in other words, you can actually connect the big B1, big B2, big B3 system to the big T1, T2, T3 system. You don't need to take both. You can take either one of them. You take the big B when you want to compare with Timoshenko theory. You just take that big T system in case you want to have a simplified just 4 variable theory, which is also asymptotically correct. So the big B1, B2, B3 is related to this big T1, T2, T3 in the case of small strain situation where the angle itself is the transverse shear strain. So therefore your 2 gamma 1 2 and 2 gamma 1 3 would come over there because the sine of the angle would be approximately the angle itself. So that is how these terms come up. So in the case where transverse shear strain is 0, that is let's say you have a long slender beam like this. In other words, the cross-sectional dimension is very small compared to the length, very, very small compared to the length. Then in such situation, transverse shear strain would be approximately 0. So the plane, the cross-section which was plane to the reference curve will remain plane to the reference curve even after the curve, after the deformation. So in such a situation, gamma 1 2, gamma 1 3 would be 0. You could see that this matrix, 3 by 3 matrix here, would become just an identity matrix because there are only 2 non-zero terms on either side of the diagonal, and all 4 of them will go to 0, and therefore you would have an identity matrix. So B1 will be T1, B2 and B3 will be T2 and T3 respectively. So the difference comes only when you have short stubby beams, and which is a rare situation, but many stringers could be like that. So whether you have that or not, the theory will automatically take care of it depending upon the relative orders of magnitude of the various quantities. So this is just introduced to show the distinction between introducing a coordinate system in the deformed configuration, which is associated with a reference curve tangential, that is T, or with respect to the cross section, namely B1, which is perpendicular to the reference cross section. So I think one more thing that I wanted to show over here is that, as I said, in the case where you introduce the big B system, you have all 6 of these. That is the 3 gammas over here and the 3 kappas over here. So the only difference when you go to the T system will be that these 2 will be absent, but then your small gamma 1 1 and the kappas will take different meanings. Okay. So because they are containing the transverse shear indirectly through the warping it is coming, and the warping is a function of the 1D strains as well. So therefore we will deal with just a 4 by 1 column matrix which involves only one translational strain, namely the extensional strain. The transverse shear strains are not necessary, and they're which are included in the warping already. So it's an alternate way of including them. And of course you have the kappa I. But now we are representing them with a bar to indicate that they are different from the gamma 1 1 and the kappa I that you see here in the big B system. So just by changing the coordinate system, you are changing the meanings of these variables. You will change the values of the warping also, but the total will remain the same. That is, your big R hat will remain the same whether you're modeling with your big B system or big T system. Your modeling paradigms do not in any way affect the end results, the 3D fields of displacement, strain, stress. They will always remain the same. But when you have the 4 by 1 quantities, the way they are related to the 6 strains, 1D strains that we already had, is that you are just setting the 2 gamma 1 alpha equal to 0 because you are including that elsewhere, that is in the warping. So instead, when you include it in the warping, the strains get a different meaning. The 1D strains get a different meaning. So with this slide, I will not further go beyond to talk about these barred quantities. We will only talk about the unbarred quantities, that is the 3 strains associated with the translations and the 3 Actually, rotations are involved over there, over and of the cross section over and above what plane perpendicular to the reference line did, and then the curvatures. So we will continue with the 6x1 system just to show the parallel with the Timoshenko beam theory as well. So now that's as far as the kinematics is concerned, the 1D kinematics. We will also look at the 1D constitutive law next. But before that, I'll introduce a certain notation called the tilde notation, which is also called as a dual matrix. So instead of a column matrix or a vector, we are introducing in its place a dual matrix, which is usually very convenient to carry out the cross product. See, already we moved from a derivative with respect to x1, any derivative with respect to x1, we said can be thought of as a cross product with the k, small k in the undeformed and the big K in the deformed configuration. So bi prime, for example, became small k, small bi prime became small ki crossed with small bi. Similarly, the big bi prime became the big K crossed with the bi. So we already said that a prime can be replaced by a cross product. Now we are going one more step in simplifying that. A cross product of two vectors can be replaced through a matrix multiplication. That to introduce that matrix multiplication instead of the cross product, we introduce this so-called dual matrix through a tilde notation. Now what is this? Fairly simple. Suppose you had any arbitrary vector. Let's take, for example, that velocity vector that we are talking about of the aircraft, let's say, or any arbitrary vector v. So the vector v, when it is expressed as it is written in bold font in printed text. But when we write it in our notes, we will put an underline over here, a single underline, to show that it's a first order tensor, namely a vector. And that we will dot it with another vector, namely the unit vectors of a chosen reference system. In this case, let's say big BI. It could be small bi or small ai associated with the A-frame, or a small ii which is associated with the earth fixed inertial reference frame. It doesn't matter. But once you fix that, you are going to get that measure numbers. So these are called the measure numbers VBI of that vector V about a given set of reference curves, that is reference unit vectors, which is big B1, B2, B3. If you change this B to let's say a small b, then small bi's, then you would have this as the small v along the small bi system. So that mentioning whether it is with respect to big B or small b, or with respect to A or with respect to I, that is very, very important. So that is one thing. Next, we can express these VB1, VB2 and VB3 that we get by dotting with big B1, B2, B3 as a column matrix, which can be written as a transpose of a row matrix. So VB1, VB2, VB3 transpose is your VB. So it's basically a 3x1 column matrix. Now you see that I'm removing that I subscript over there, which was required for the scalar quantities, which are the measure numbers. Instead of that, I have gone into a column matrix VB. So I'm using the same notation V and B, but now I'm dropping the subscript I, which is the free-flowing index over there. Now, now we introduce the tilde notation of the dual matrix. We say that for any vector V expressed in a particular basis big B, its tilde or a dual matrix is given by an antisymmetric matrix, in which all antisymmetric matrices, as you know, will have the diagonal terms going to 0, and about the principal diagonal you would have the elements which are the ij element would become negative of the jith element, so they would interchange only the sign. So it's the same three quantities, 1, 2 and 3, put in this order going from the bottom upwards. Same way here also, 1, 2 and 3, but with a particular way of putting the signs. These two are negative and this is positive, so therefore this becomes negative. So this is the tilde notation, and this can also be written in an indicial form using your EIJK, where Eijk small e refers to a third order tensor, which is going to be 0 if there is any index which is repeated. So in other words, for example, let's say 111 or 222, if ijk take on those values, or 333 or 112 or 121, like that, in at least one index is repeated, then you would have, or all indices are repeated, then it goes to 0. If it is a cyclic order, like let's say 123 or 231 or 312, if it goes in that cyclic order, then the value of that Eijk becomes 1. And on the other hand, if it is acyclic, so let's say 213 or 132 or 321, so in all of these cases, it goes to -1. So this is just an alternate way of writing the same dual matrix that I've written in the white background. That is VB tilde, now the ijth component is going to be given by minus Eijk multiplied with VBK. And of course, there is an implied summation over this repeated index, which is small k, which is a dummy index. So over k equal to 1, 2, 3. So when you do that, automatically you will get the elements of this matrix. So there's just two ways of expressing the same thing. So instead of having to cross with this vector v, we can now multiply with this VB tilde and we would get the same result. Let's see some examples of this dual matrix notation or the tilde notation. Suppose you have a vector which I call as E1, 1, 0, 0. Now all that I have to do, I know that the first element, that is okay, so the first element over here is 1. So in other words, in place of VB1, I have to put 1 over here, and the rest will all become zeros. So these would become zeros in this particular example that we have over here, whereas this would become 1, and because of this minus sign, this would become -1. So that's basically what you have as E1 tilde. So this is just an example of how the tilde is basically applied, and equivalently you can check, cross verify that if you use this initial notation also, you'll end up with the same elements for E1 tilde. Another example, so this E1 we will use, the reason why I introduced this example is this E1 is a quantity that you will see frequently used in the equations. So and similarly your E2 will be let's say 0, 1, 0, and your E3 will be 0, 0, 1. But these are not used in our derivations. This is something that you will see often, and therefore E1 tilde as well. So next, another example, let's take the X bar. Okay, X bar is, let us say, the location of the centroid, mass centroid of the cross section. See, area centroid is different from mass centroid. Area centroid will only look at integrating xdA divided by integral dA, which is the area, whereas here you take the density also inside as a weighting function to get the mass centroid. You're familiar with that from the basic middle school mathematics. Now, as far as the choice of reference curve is concerned, we said that we may not always choose the reference curve as the loci of the mass centroid. It could be the loci of the area centroid, it could be the neutral axis, shear center, center of twist, whatever. Leading edge, trailing edge, according to our convenience, aerodynamic center, whatever. So in general, the mass centroid of a cross section will be at a different location from the reference curve. So the distance from distance of the mass centroid from the reference curve on a given cross section will be x2 bar along the x2 axis and x3 bar along the x3 axis. So we have a column matrix 3 by 1. That's why the transpose of a row matrix. So you have x2 bar and x3 bar coming over there, and we will call that as x bar. So obviously there's no movement along the x1 direction. We are looking at a particular cross section's mass centroid, and that is the reason why the first element here is 0. Now if this is x bar, then what is x bar tilde? So using the same matrix manipulation or using the initial manipulation over here, you can very easily see that, oops, okay, you can very easily see that x bar tilde is going to be given by, once again, zeros along the diagonal elements. The one element is 0, so this also goes to 0, and then here you have x2 bar over here, and you have correspondingly antisymmetric minus x2 bar, and here you have x3 bar, and here you have minus x3 bar. So this is another example of how you use the tilde notation. So why I'm spending so much time on this is this makes the equations far more simpler. One, we already said that derivatives no longer need to be taken into account. The derivative can be replaced with a derivative with respect to x1 can be replaced with respect to with the cross product with respect to small k or the big K. Now, similarly, instead of a cross product, we can introduce the k tilde and just pre-multiply by k tilde. So k cross something would just become the k tilde multiplied by that quantity, whatever you're using, as a column matrix. So for example, if it was that vector v that you are dealing with, that is the same vector v, instead of a v prime, we said that we can introduce a k cross v, and instead of the k cross v, we can just introduce a k tilde into that v as a column matrix, like what we had here in a particular reference coordinate system. So you have to be consistent with that. So this is the reason why it's so convenient to have this dual matrix. So let's next look at the constitutive law. So far we've been dealing with the kinematics and certain notations. Now we know that there are three sets of equations: kinematics, constitutive law, and equilibrium equations. So before we look at the big picture of all of these on one slide, let's look at the constitutive law separately. We have in fact looked at this earlier, so you will be familiar with what I write over here to start with, but I've written it in the inverse way. Usually I will write F1, F2, F3, M1, M2, M3, that is this generalized force vector on the left hand side, and the gamma 1 1 2 gamma 1 2 gamma 1 2 gamma 1 3 kappa 1 kappa 2 kappa 3 on the right side. I'm just putting the inverse of that and calling it by a set of partition matrices. So because I'm going to replace this essentially this column matrix gamma 1 1 gamma 1 2 gamma 1 3 by just a gamma, and this kappa 1 kappa 2 kappa 3 by just a 3 by 1 column matrix kappa. Similarly, this F1 F2 F3 by just a column matrix F, and this M1 M2 M3 by another column matrix M, all of which are 3 by 1. So now therefore I can partition this matrix over here, and you see that this is an R matrix over here, this is an S matrix, this is a T matrix, and here very interestingly you would see that it is a S transposed matrix, only then the overall symmetry will be maintained, and in general this S itself will not be symmetric. So in other words, S12 and S21 can in general be different from each other, whereas R12 and R21 are equal to each other, that's the reason why we are not even written R21. Similarly, your T12 and T21 will be same, etc. So the R and T are symmetric matrices, whereas S in general need not be a symmetric matrix. Many times it may be a zero matrix, in which case it is anyway zero, it is symmetric, but in general it will not be a symmetric matrix, and that's why you need to say S transpose. Even in I think especially if you go to the plate theory, classical plate theory that some of you might be familiar with for composites, ABBD. So the right way to write it is ABB transpose D, because sometimes it is possible that B12 and B21 may not be equal to each other. But the way we define that in for most classical textbooks, is that therefore B12 and B21 are equal to each other. So B is equal to B transpose. So we just say A, B, B, D. But strictly speaking, if you want a 6 by 6 matrix to be symmetric, then and it is partitioned into 3 by 3 matrices, then the off diagonal matrices there should be called with one of them with a transpose, so that the overall 6 by 6 matrix is then symmetric. So this is the constitutive law. Now this constitutive law is basically now written in a simpler form, that you have instead of a 6 by 1 column matrix, you have two 3 by 1 column matrices, namely your gamma and kappa, and that is related to another two column matrices, F and M. So recollect that gamma 11 is the extensional strain, 2 gamma 12 and 2 gamma 13 are the transverse shear strain, that is the rotation of a cross section over and above the rotation that it gets due to the joyride on the reference curve. Then you are also going to have F and M. F is basically your axial force per unit length. Axial force, which is basically the reaction of the cross section. This is not what you are applying. In some simple examples, it might be equal to what you are applying, but it is basically at any arbitrary cross section with arbitrary loading, arbitrary boundary conditions at a particular cross section. What is the axial force that is existing by integrating sigma 11 over the cross section? That is basically your F1. Similarly, your F2 is a tau 12 integrated over the cross section. Similarly, your F3 is nothing but tau 13 integrated over the cross section. These three normal and shear stresses acting on the one surface when integrated over the cross section lead to F1, F2, F3. Similarly, they can also create a moment resultant, which is what M1, M2, M3 are all about. M1 being the torsional resistance of that cross section, M2 and M3 being the bending resistance, what we call as the bending moment. Again, the bending moment need not be what you are applying as an applied moment. It could be, it is basically the reaction of the cross section through its stress distribution. In particular, the sigma 11 distribution is what will cause your M2 and M3, whereas the shear stresses, namely tau 12 and tau 13 multiplied by their moment arms and the elemental areas where they are applied, will give you the torque, that is your M1. So this is a much simpler way of writing the same equation, that gamma kappa is equal to R S S transpose T multiplied by F and M. But this is good enough as far as a statics problem is concerned. But we know that we are not dealing with a statics problem. Things are moving, and the beam, namely the wing or spar or stringer, is vibrating. And therefore, there is a change with respect to time as well. If that dynamics were not there, all the equations, everything will be ordinary differential equations, because only x1 is left. x2 and x3 have been eliminated, the cross-sectional coordinates. All that we need to deal with is x1. We will have only ordinary derivatives and ordinary differential equations to deal with. But in a dynamics problem, time will also come in, and therefore you have a space-time problem of x1 and time, and therefore partial differential equations, partial derivatives will be critical. So just in analogy with this constitutive law for statics, we have a constitutive law for the dynamics as well. Now, what is that analogy? We will see now. So in the constitutive law for statics, what we had is, we had the strain gamma and the curvature kappa. So in its place, we will now introduce, instead of gamma, we will introduce a velocity v, and instead of the curvature kappa, we will introduce an angular velocity omega. And instead of the force that we have over here, we will introduce the translational momentum, which I think will denote by P. And instead of the, so in a dynamics problem, and instead of the moments, we would have the angular momentum, which is H. Then of course this matrix will also change. You'll no longer have RS S transpose T over there. So let me clear the pen markings, and now introduce you to what is the equivalent of this constitutive law in the case of the dynamics, what happens. So we now have, instead of gamma 1 1 2 gamma 1 2 gamma 1 3, we have P1 P2 P3, that is the measure numbers along big B1 big B2 and big B3 of the translational momentum. And similarly you have H1 H2 H3. So here I have actually inverted, that is F and gamma I have inverted for a particular purpose because we'll be using it in this particular form, but here I have not inverted that. So the correspondence is actually between P and F over there and between H and M over here, and similarly between the gamma and the V you'll see a 1-to-1 correspondence, and between kappa and omega. So in other words, I'm saying that when you're looking at dynamics, you don't need to look at it as a separate topic. If you understand statics properly, you can extend it to dynamics sheerly through analogy. And that's the beauty of this whole set of equations. We'll see that further analogy as we develop this further on. So in the same way that we simplified it into a smaller set of matrix equations, we can do this for the momenta as well, that P and H can be written in terms of V and omega, where P and H are now 3x1 column matrices, so are V and big omega, big V and big omega, and they are related to various quantities there. So now let's look at what those quantities are. So here, again, if I partition this matrix into 4 3x3 matrices over here, once again it is symmetric about that. So essentially all of this are coming from a variational principle. So where does this come from? This comes from a strain energy density U3D per unit volume. Similarly, this will come from a kinetic energy density per unit volume, that is again in joules per meter cube. So from the kinetic energy we can derive this, just like from the strain energy we can derive that. As I said, I'm not going into the details of the derivation, which is for the next course, which is a logical extension of this, but we will only give the end results. So here if you see these 4 sets of matrices that are involved over here, once again that you see that there is a minus. That's why here you can see very clearly that this quantity is not equal to this quantity. This is negative, this is positive of each other. So, and that's why I was telling it's so important to put this transpose over here. Whereas the overall matrix is symmetric. Just like this also, overall matrix is symmetric. And similarly, R and T are symmetric. Similarly, this submatrix and this submatrix are all symmetric, but this off-diagonal partition matrix is not symmetric. So now there are a few notations that I have introduced here that I have to explain. So there is something called mu, which is nothing but mass per unit length of the beam. So usually it is made out of different materials. As you know, we saw examples of a helicopter rotor blade which is made out of a steel cap and a graphite epoxy composite, a glass epoxy composite closer to the trailing edge, graphite epoxy for the spars, and then foam for a sandwich construction towards the latter half of the airfoil. So when you have different materials like that, each of them is going to have a different density. So you have to multiply the density by elemental areas and integrate over the entire area numerically and divide by the overall area of the cross section in order to get the mass per unit length. So that is basically you don't divide by the area, you just integrate over the area to get you integrate the density distribution with respect to the cross-sectional area in order to get this mu. So mu is the mass per unit length of the beam. Similarly, your I2 and I3 are the mass moments of inertia. Once again, the density is weighting that. So remember that you are familiar with the area moments of inertia, which is what you used in getting, let's say, EI2, EI3, etc. The I2 and I3 that you used for the bending stiffness are area moments of inertia. Here we are talking of mass moments of inertia. In other words, there is a density factor also which gets into it. So that is basically that, because we are talking of kinetic energy and we are talking of how the angular momenta h are related to the angular velocity, and therefore you would have the mass moments of inertia coming into picture instead of the area moments of inertia. So that's basically your small I2 and I3. They are also per unit length. So because we are talking of the cross-sectional behavior, so at a given cross-section, what is it per unit length? Because we are dealing with kinetic energy per unit volume, we integrate over the cross-section, we get kinetic energy per unit length, and similarly all the quantities which are the multiplying factors in this overall 6 by 6 matrix also become per unit length. So that's your I2 and I3. Those are mass moments of inertia. Then if you do not have a symmetric distribution of the materials and or the geometry of the cross section, either because of an unsymmetric airfoil or because of the way you have positioned the stringers, or because you have the top flange and bottom flange of the spar different from each other, etc., and you have chosen a particular point as the reference curve, reference cross section intersection, which is not on the plane of two planes of symmetry, then in all those cases you are going to have what is known as a mass product of inertia as well, which is non-zero, which is what you see over here. So this I23 that you see over here is a mass product of inertia. That is, you will be integrating x2, x3 over the cross-sectional area after multiplying it by the density rho, which is varying along the cross-section. So rho integration of area integration of rho into x2 into x3 into dA, which is also dx2 dx3 in a rectangular Cartesian coordinate system. Therefore, that basically is your I23. Similarly, you're talking of not necessarily choosing the so this is all that you would have had if you had chosen the mass centroid as the reference curve. So no other off-diagonal terms would be there. But once you have chosen, let's say, aerodynamic center or some other point loci as the reference curve other than the mass centroid, then you know that x2 bar and x3 bar, which we introduced earlier on the cross section, are going to be non-zero. So in other words, x2 bar and x3 bar are the location of the mass centroid from the reference curve on a given reference cross section. So that x2 bar and x3 bar being non-zero brings in some coupling between translational momenta and angular velocity, and between angular momenta and the translational velocity. So that is between h and v and between p and omega. There is a coupling which happens now, and that is going to be given by the mass per unit length multiplied by those x2 bars and x3 bars that you see with the appropriate signs. So all these quantities, of course, the overall matrix is symmetric. So this comes into play as well. So this is basically the most general form that you can have for any arbitrary unsymmetric airfoil cross section with very complicated material distributions of composites, different hybrid composites, and with sandwich constructions and with metallic components. Doesn't matter, and you have the dynamics taken into account because of this particular generalization of the constitutive law. People generally talk of constitutive law as just this, but that's for statics. Once we bring in dynamics, you need to understand how the mass behavior, the inertial behavior is coming into picture as well, and that's why this mu and I2, I3, I23, mu times x2 bar and mu times x3 bar are all going to make a contribution there. And you can very easily verify from what we discussed in the previous slide that we can just replace this by an x bar tilde, which we wrote expression for that 3 by 3 matrix in the previous slide. So we can instead use that and make this notation much more complicated, much more compact. And then also this first partition matrix here, you can see, is nothing but an identity matrix multiplied by the mass per unit length, and we will denote delta as the 3 by 3 identity matrix, and therefore mu times delta becomes that 3 by 3 matrix that you have here. And this we will denote by I, That's why we didn't use I for identity. This is delta is identity, and I is the inertia matrix. That inertia matrix consists of I2, I3 as the 2, 2 and 3, 3 terms, and that sum of I2 and I3 as the 1, 1 term. Okay, so I2 plus I3 becomes your 1, 1 term. The mass moment of inertia about the x1 axis has contributions from both the distributions about the x2 and the x3 direction, and that's why you have your I2 plus I3 like that. So because we are talking of all these quantities of a planar area, that is the cross section, and in a sense of a mass per unit length, the planar cross section by itself is of zero thickness, which means it will not have any mass per se. So that's why we are all talking of all these mass per unit length, because that's what the cross section essentially denotes, because of the continuity along the reference curve of the cross sections. So this is as far as the constitutive law is concerned. Are there any doubts or questions on this? Okay. So now we'll assemble all of these things that we talked about in bits and pieces, along with a few more information that we didn't talk about, because those are much simpler to deal with. So the most complicated portions are all taken care of now. Now we have to deal with these equations. In the next class, we will look at the equivalent 2D values, 2D state of the art, and also we will look at what is it in the 3D, which is valid for all kinds of structures, including beams, shells, plates, etc. So now you can see that it's the same set of 4 quantities, namely loads, the stresses, the strains, and the deformation that we want to relate. But the difference is now, earlier used to talk about in 3D sense, now we are talking everything in a one-dimensional sense. So this qualification, you can see 1D load, 1D stress, 1D strain, 1D deformation. 1D strain we already looked at in the when we looked at the schematic of the deformation. We introduced that gamma and kappa. So those are basically your 1D strains. That is the 3x1 matrices involving gamma 1, 1, 2, gamma 1, 2, 2, gamma 1, 3, kappa 1, kappa 2, kappa 3. So those two column matrices, gamma and kappa, are your 1D strains. What about 1D deformations? They involve not only small u1, small u2, u3 of that u vector, which was from the small r curve, the undeformed curve, reference curve, to the deformed reference curve big R, we drew a vector which is u, so that the small r vector position vector became the big R position vector by just adding that small u. And that translation is one of the aspects of the 1D deformation, but not that alone. You also have the each cross section rotating by different amounts about the x1, x2, x3 axis. So that contributes the deformation as well. In other words, theta 1, theta 2, and theta 3. So either you can think of them as 3 rotations, theta 1, theta 2, theta 3, or you can think of them as the let us say the direction cosine matrix elements, etc. But essentially that's what it is. So in other words, we have to relate that C to the kappas over there. So that is what we will see. And now the relationship between these quantities, relationship between these quantities, between the loads and the stresses are the equilibrium equations, between the stresses and the strains are the constitutive law, and between the strains and the deformation is your kinematics. Again, all of them are 1D in the sense that they are all going to be dependent only on the x1 coordinate. x2 and x3 have already been incorporated through that constitutive law, which was an integration over the cross section of the kinetic energy and the strain energy, lumped in through, let's say, mu, I2, I3, and your RS and T transpose matrices that we saw relating between the 1D strains and the 1D resultants. We saw F and M, we saw all those things introduced. So that's basically going to be your constitutive law. And eventually the 1D kinematics, which relates the 1D strains to the 1D deformations. Now, what are 1D stresses? The 1D stresses are stress resultants actually. And that's basically your axial force, your the shear forces, the torsional moment, and the bending moments through which the cross section resists the applied load in the presence of certain boundary conditions. So once again, clearing that, let's see what these are explicitly. Now, the loads can some of them can be concentrated loads, some of them can be distributed loads. We saw in the case of the aircraft, we saw that the engine weight, for example, is a concentrated load. Actually, it's distributed over a small area the way the engine is attached, but for most practical purposes, we can think of it as a concentrated load. And then the thrust is a concentrated load, but the lift distribution and the drag distribution are distributed loads. So these are two kinds of loads. One is concentrated, the other is distributed. The way we take care of them is very different in this paradigm. Both are applied loads. These are coming from external to the wing. And of course, the wing's self-weight will be there and so on and so forth. We can take that as also. Now, again, that's a distributed load. Of course, in addition, there will also be the moment about the aerodynamic center, and if it's undergoing any, let's say, banking, and because of which it is rolling, and therefore this is coupled with the yawing as well. So all of those moments and other things will be there as well. But essentially, you can have two types of loads, distributed and concentrated. As far as distributed are concerned, they enter the governing equations itself, that is the equilibrium equations. But as far as the concentrated loads are concerned, they become boundary conditions. They may not be necessarily at the tip. In the case of the engine, for example, it's somewhere in between the wing. But still, it's basically breaking up the entire beam into parts, and it's an intermediate boundary condition that you have. So all of these concentrated loads will appear as, or let's say there is a simply supported beam, as in the case of the fuselage over here, which we are considering as a simply supported beam with an overhang over here. And this is basically one hinge, and this is another hinge, one of them on rollers, the other is fixed. And so basically you're seeing it as a simply supported beam over here. So then the reactions that are coming at the simple supports, they are basically boundary conditions. For the wing or the tail, these are cantilevers, and the way they are attached to the fuselage, the reactions that come from the fuselage there, that is basically boundary condition again. So essentially what we are talking about is the 1D loads. We can talk of the concentrated loads separately as boundary conditions. So let's not deal with them right now, because we are going to deal with differential equations, and differential equations, to solve them as a boundary value problem, we will need boundary conditions, and that's one set of boundary conditions, the other set coming from the specification of the displacement field or the rotations at certain locations. Like the fixed length, the rotation and displacement are zero. At let's say a hinge, you have both types of conditions. One is that the moment is zero, which is a force-like condition. The other is that the displacement is zero, which is at a hinge, which is displacement perpendicular to the beam. That is basically a displacement kind of boundary condition. So the 1D loads that we are dealing with are the which enter the differential equations, but not the boundary condition, but the differential equations are those which are distributed loads, like the lift distribution or the drag distribution. So therefore, we are again dealing with them as per unit length. So that is lift per unit length, drag per unit length. These are all put together in your F matrix that you have over here, and the moments, like for the pitching moment per unit length, etc., these are coming into small m. So all the distributed loads, including the wing's self-weight, if there are things inside the wing like the fuel and the control surface, etc., all the loads that are created by them, whatever is distributed, is all lumped into this. Again, we are talking of 3x1 matrices. So we are talking of small f being F1, F2, F3, where F1 is along the axial, the loads along the axial direction, which is not there in the case of a aircraft, but if it's a helicopter rotor blade, then you know the centrifugal forces, for example, are coming over there. So at a given cross section, the rest of the length from that cross section to the tip, that is trying to pull apart. So that is basically causing a axial force distribution at that cross section how it will resist that centrifugal loading. So that's going to be as part of that as well. So your small f and small m are both column matrices, f1, f2, f3, and m1, m2, m3. And m1, m2, m3 refer to your torsional resistance per unit length, and the bending moments, which are also resistances per unit length, which are created, of course, by the sigma 11, tau 12, and tau 13 distributions on that particular cross section. Similarly, your F2 and F3 are shear force, what you get from your shear force diagrams, for example. So here, this small f and small m are the applied loads. These are not the reactions. Now we come to the section forces and moments, which I was just describing to you now. That is basically your axial force and two shear forces, F1, F2, F3, and similarly your moment, which is M1, M2, M3, M1 being the torsional resistance, which is offered through an integration of tau 12 and tau 13 with the appropriate moment arms, and your M2 and M3, which are your bending moments, which is sigma 11 multiplied by the distance from the neutral axis integrated over the cross section, which is going to give you M2 and M3 about the x2 and x3 directions respectively. That's good enough for statics problem. What for a dynamics problem? You need to further introduce the sectional linear momentum per unit length P, again consisting of P1, P2, P3, which we saw in the previous slide, and the angular momentum per unit length H1, H2, H3, once again about the x1, x2, and x3 axis. The next set of variables are the 1D strains. What are they? They are gamma and kappa, where gamma is gamma 11, 2 gamma 12, 2 gamma 13, again a 3 by 1 column matrix. So unless otherwise specified, all variables that we are dealing with here are 3 by 1 column matrices, right? So similarly, your kappa is kappa 1, kappa 2, kappa 3. So gamma includes the extensional strain and the two transverse shear strains. Your kappa includes the twist per unit length and the two bending curvatures. Next, you talk about, in a dynamics problem, instead of gamma, we have a V, or in addition to gamma, we have a V, and in addition to kappa, we have another quantity, big omega. This is the translational velocity of that point, which is the intersection of the reference curve with the reference cross section. That point is undergoing a certain velocity with respect to the inertial frame of reference. In other words, with respect to an earth fixed frame, which takes into account both the motion of the aircraft and the motion of the cross section on that aircraft. And in the case of a helicopter rotor blade, the rotation as well. So all of this will be included in your big V and your big omega, the motion of the aircraft and the motion of the, in the case of V, the point, and in the case of omega, the cross section. The point on the reference curve and the, which is the loci of, let's say, whatever you have chosen, and of the reference cross sections. Finally, this you may or may not need, depending upon whether you're going through a regular formulation, which is also geometrically exact. In other words, there's no approximation made with respect to the 1D geometry, as we discussed in the last class, but it could also be fully intrinsic. What does fully intrinsic mean? You can completely leave out the displacement and rotation variables and solve the problem entirely, and later get their displacement and rotation variables along any particular coordinate system or any particular definition of the rotation variables that you might want after the entire problem is solved. So it can be done as an as a post-processing. So right now I'm not looking at that fully intrinsic formulation. This is a regular conventional formulation where you introduce explicitly the displacement and rotation variables, just to show you that the importance of this fourth category of variables, without which also we can solve the problem. So here, what are they? U1, U2, U3, which we'll put in a column matrix, but if it's represented in a vector form, it's basically your U of x1. In a dynamics problem, it's a function of time as well. What does it do? It moves a point from the undeformed reference curve to the deformed reference curve. That's all that U does. In addition, you have another set of 1D variables, which are deformations as well, which are your rotation variables, which help populate the direction cosine matrix. It's a 3 by 3 matrix involving 9 elements, but they're all functions of just theta 1, theta 2, theta 3, 3 rotations, let's say we start with the rotation theta 1 about the b1 axis, small b1 axis, and then you come up with a new intermediate reference frame about the 2 direction of that. You have a rotation theta 2, you have one more intermediate frame of reference with respect to the 3 axis of that, you have one more rotation, and so after all these 3 rotations you end up with the pink or orange plane that we had in that schematic. That is basically what we are talking about. Using just those theta 1, theta 2 and theta 3, we can populate your direction cosine matrix, as you're familiar from other courses including flight and space mechanics. So your Cij can be obtained by Bi dot Bj, but the fact is we do not know Bi. So all that we are talking about is in terms of unknown quantities, theta 1, theta 2, theta 3. But actually what this equation helps us in getting big Bi if we know Cij by multiplying it with the small b system. So that's basically what this helps in. So now we have understood what are these 4 sets of variables in a 1D problem. Now let's go ahead and see what are the equations which relate these. That is, the small f small m with the big F big M, whatever relates, that is your equilibrium equation in statics. But in dynamics, it should also bring in your big P and big H into the picture. Then you have to relate the stress to the strain, that is your Fm, P and H have to be related to gamma, kappa, V and omega, which we already did in the previous slide. And from that 6 by 6 matrix, we came to a compact partition matrix expression, which is what we will repeat as far as the constitutive law is concerned. Then strain to deformation relationship, that is how are gamma, kappa related to u and theta, and how are v and omega also related to u and theta. That is basically what we will see in the 1D kinematics. Let's see what these equations are. Now, this is a very, very beautiful equation. Unfortunately, I do not have the time to derive it. It basically comes from the Hamiltonian principle. Applying the Hamiltonian principle, we can get the governing differential equation, which involves your axial force, your shear force, your torsional moment, your bending moment, how they are related to the distributed load, not only in a statics problem, but in a dynamics problem involving translational momenta, angular momenta, and their variations with respect to time, the velocity, angular velocity, etc., and the curvatures which ensue, and the strains which are coming over there. So you see that this is the equilibrium equation which is relating your load, which is your distributed load small f and small m, which is because of your lift distribution, drag distribution, self-weight distribution, other payload weight or fuel weight or other control surfaces, electrical weight, etc. Any distributed load which is lumped into your small f and small m along 3 different directions. You have f1, f2, f3, small m1, small m2, small m3. These are now causing your big F and big M. Now, what happened to the concentrated forces? Remember that these are differential equations. You cannot solve them you can't get a particular solution unless you use the boundary conditions. So when you do that, that's when the concentrated forces will come. They do not affect the governing differential equation itself. So all concentrated forces are left out of this governing differential equation. If you have to solve them in a general sense, concentrated loads will not matter at all. It's only small f and small m which will matter. And small f and small m may not exist throughout the length. There are certain parts through which f might be 0, some parts where it may not be 0, and we have to take all of that in a functional form, how it is varying along x1, how it is varying with time in the performance of a certain maneuver, which could involve, let's say, a pull-up. So the dive loading might be different. In the pull-up at the bottommost, it might be different. Again, when it comes to the top, it might be different. The load factor itself is different, as we saw in the flight envelope when we discussed that. And therefore, all of that comes into understanding this small f and small m. So that's where there's used to be a separate department in aircraft companies or spacecraft companies called the loads department, where loads engineers used to estimate all those loads from either let's say flight test data or the typical conditions. If it's the aircraft still being designed, based on the design parameters of the aerodynamics, you estimate all these loads, small f and small m, which is basically the loads. Once you have that, now we want to see as a structural engineer what is going to happen to this particular beam, how it's going to resist that, how is the wing going to resist those external loads that you're applying, small f and small m. Now that's where the beauty comes. Again, I'll go in steps over here. You see, you can combine these in pairs, f prime plus k tilde f. Similarly, you have m prime plus k tilde m. And on the dynamic side, you have p dot plus omega tilde p, and you have a h dot plus omega tilde h. Now look at the beauty of this mathematics that is involved over there. With space, you have derivatives with respect to x1, that is your primes. And then there's a further thing that is happening because of the curvatures. That is where this multiplication with the tilde quantity of the curvature comes in. In the case of the force resultants, it is k tilde which is multiplying. Same thing with m. The force, the moment resultants are multiplied by k tilde. But the role that k tilde or the curvature plays in space, the same role omega, big omega, plays in the case of the dynamics. So you see that multiplication is now done instead of by k tilde, by omega tilde. So there is a 1:1 correspondence between space and time, which is why our ancient scriptures called space-time together as kala. So that beauty is there in the mathematics of the equation itself over here. And similarly, your primes are now replaced by dots. So that is the variation with respect to x1 is now a variation with respect to time. And wherever force is, you will find the translational momenta, and wherever the moment is there, you will find the angular momenta. And that is what you are familiar from your generalization of Newton's laws as well. What does Newton's law say? Of course, in the simplest form in school, you would have studied as force is equal to mass into acceleration. But essentially, the force is the rate of change of the momentum. So that's basically what is happening, how the momentum changes with respect to time. Similarly, the moment is nothing but the rate of change of the angular momentum. So in other words, your m has to be related to your h dot, and similarly your f has to be related to your p dot. But now, because we are dealing with a continuous system rather than a rigid body dynamics over here, there is a variation which is happening along x1 of this beam, and the problem has broken into two parts. One is the cross-sectional analysis, the other is the 1D analysis, and in the 1D analysis we are dealing with these quantities over here. So that is your small f, small m is related over there. Now, in addition, there are some things which complicate the issue, especially in the moment, because there is rotation involved, and therefore the angular momentum as well. And those are these additional terms that you see. But once again, you will see a parallel over there, that the role that gamma tilde plays, or gamma plays in the case of the space, the same role the velocity plays over here, which is why if I multiply by gamma tilde here, I have to multiply by v tilde. But then why this E1 tilde is coming? Because already there was an existing aspect of where that cross section was along the length of the beam, and then over and above that it had a u displacement, and which is why with respect to, let's say, the fixed end of the cantilever beam of a wing, let us say, you're basically dealing with that, and therefore that E1 tilde is coming as an additional thing. But if you look at what essentially it is basically coming only in the first term. That is because E1, that is 100 is that column matrix from which E1 tilde is obtained. So in other words, there's nothing happening with respect to the x2 and x3, which we can see because that cross section is different from cross section at the root only by how you're moving away from that particular cross section along the reference curve, which means only x1 is changing. That's something I described using a cantilever, but the same thing holds in the simply supported or any other boundary condition beam also. One end, which is x1 equal to 0, if we take that as a reference, with respect to that we are looking at all the other cross sections all the way up to x1 equal to L. So this is basically your 1D equilibrium equations. I know I'm close to ending. I'll just finish with these two sets of equations, which we already introduced in a previous slide in terms of the constitutive law, how gamma and kappa are related to F and M, and how P and H are related to V and omega, and that's what you see over here. And then finally the 1D kinematics. What does the 1D kinematics have to do? It has to relate this gamma and kappa to u and theta. So because gamma and kappa are the strains and u and theta are the deformations. So that's basically what you see in this equation. Let's start with this particular equation that you see over here. You see that the big K, that is the curvature in the deformed configuration, is related to the direction cosine matrix, which in turn is a function of theta 1, theta 2, theta 3. So basically we are relating the elastic curvatures to the direction cosine matrix, and therefore to the rotations theta 1, theta 2, theta 3 of the cross section. Now how is that being related? By a C prime C. Okay, again all these derivations I have not done, which will be done in the next course, but here we are just presenting the end results, and people even without knowing those derivations can actually use these results to solve certain problems. That's the reason why I'm presenting only the final results, especially for those who are not going to continue with structures, so that they have some kind of a takeaway or from this particular course. So the entire course, all the topics that were introduced, the terminology that was introduced, was basically to create a foundation to introduce this big picture, so that you know that there is a way of geometrically exactly solving this one-dimensional problem without making any assumptions about the geometry. The only assumption came in deriving this R S S transpose T, which is from the variational asymptotic method, which I described only qualitatively in words. So VAM, when you apply to the strain energy per unit length of this beam, and you minimize that with respect to the warpings and substitute for the warpings in terms of the strains, you end up with that. So that is the only place where an approximation is made, and that approximation is also an asymptotically correct approximation, because it comes out of the small parameter, namely cross-sectional dimension being small compared to the length. So that alone leads to that particular simplification. In addition, if you have other small parameters like the maximum strain, etc., it further simplifies. But you will end up with asymptotically correct results, and there can be better and better approximations to this matrix RSS transpose T by going to higher orders of approximation, and more often than not, you don't require anything more than the first order approximation, a zeroth order approximation, which is classical theory, and a first order approximation. More than that, you rarely, very, very rarely, maybe purely for academic purposes, but not for any actual engineering application in the industry, you would not need beyond that. So you get very, very accurate results on par with the three-dimensional finite element analysis using really high-end commercial tools. Whatever you get with the state-of-the-art that is there in 3D finite elements, you can get at 100th to 1000th the CPU time by using this. So next, we also have another kinematic equation, which is relating your gamma to the U. So that's basically this. You can see that if there is no rotation, then C would be an identity matrix, which is a simple special case. We use delta for the identity matrix. And so you would see that it's just E1 plus U prime. And if there is no initial twist or curvature as well, this would go to 0. Then you can see that gamma is just U prime. Okay, because E1 minus E1 will cancel out each other. So you see that only U prime remains. So in a simple case where there are no rotations at all, only translations, you see that gamma 11 is just U1 prime, gamma 12, gamma 13 are just U2 prime and U3 prime. That's the simplest case. But once rotation sets in, you see that the other complications. So in other words, the translational strains gamma are not related only to the translational displacements u, but also to the rotational displacements theta through the C matrix, that is the direction cosine matrix. And eventually you can extract out the elastic curvatures, that is elastic twist and elastic bending curvatures from this k minus k, that is the final curvature minus the initial curvature. Again, these are all 3 by 1 matrices consisting of kappa 1, kappa 2, kappa 3, big k1, big k2, big k3, small k1, small k2, k3. Only the C matrix is a 3 by 3 matrix, the direction cosine matrix. Now this, as far as static kinematics is concerned, the last equation that I will have for today is the dynamic kinematic equations. That is basically your omega tilde and v are going to be related to the u and theta. And again you see this beautiful parallel coming along between wherever the prime was there, you see that has been replaced with a dot. And wherever a multiplication by the k matrix was there, small k has been replaced by small omega. That is basically initial twist and curvature. Whatever role it plays in space, the same role is played by the vehicle's angular velocity in the case of time dynamics problem. Same way, you see that the role played by the spatial derivatives, as we saw before, is played by the time derivatives over here. And in this also you see that instead of u prime, you have a u dot, and the role played by E1, which is a fixed column matrix 1, 0, 0, is played by the vehicle's velocity, that is the aircraft's velocity, or in the case of a helicopter, the hub's velocity, v1, v2, v3. So that it's over and above that the dynamics of the beam itself builds up. So that's why you have E1 analogy with the V, and I guess I've completed all the other analogies. So with this, I leave this set of equations. So we can look at simplified forms of this, because each of these can break up into 3 scalar equations. So each of these equations, this first equation for example, leads to 3 scalar equations because f1, f2, f3 are involved. Similarly, second equation involves m1, m2, m3, so 3 equations. So from each one of these you have 3 equations, and in this matrix also, you know, these are 3 by 3 matrices, so you have 3 plus 3, 6 equations over there. And similarly in your gamma and kappa, how they are related there also, and your omega and v, they're also 3 equations each. And all of these are unknown quantities, big F, big M, because only small f and small m are what the loads engineer has given you. So big F is unknown, big M is unknown, your gamma is unknown, kappa is unknown, P is unknown, H is unknown, big V is unknown, and big omega is unknown. Small v and small omega are of the aircraft which you have got from flight and space mechanics. So these 9 quantities are there, all of which are having 3 components each, namely 27. So you have this small u and small theta as well, and then all of these equations can help you solve them, but only in a general sense. Then you will have to, in addition, apply the force equilibrium equations along with this, and the geometric boundary conditions along with this. So once you do that, you have the entire framework to solve any problem related to the aircraft wing. If it is complicated, you can solve using finite element analysis. If it is simple, like let's say a stringer or a spar, you might even solve it by using closed form analytical solutions. But be it the wing, be it the fuselage, a helicopter rotor blade, or interior components such as spar, stringer, etc. in the wing, tail, or the fuselage, you can solve all of them by using this set of equations, given small f, small m by the loads engineer, given the small omega tilde, small omega, and the small v, which is the aircraft's angular velocity and aircraft's CG's velocity. Then using that, you can from the flight and space mechanics, using that as the input, you can solve this entire problem. Of course, you need the boundary conditions to arrive at the final results. So thank you very much. With this, I complete today's class of the 1D state of the art in the theory. We had a glimpse of the 1D theory only in terms of the final results, but to make you understand those final results in terms of the meaning of the variables, I needed to give a little bit of a preamble without going to the derivations, but making you very clearly understand, I hope, the meanings of all the variables. So in this coming Thursday class, we will have let's say the 2D theory state of the art, again part of it, and then we'll go into the aspects of 3D elasticity in the same framework. That is that big picture of load, stress, strain, displacement, and the equations relating them, equilibrium, constitutive, and kinematics. In the same framework, we will look at 2D and we will look at 3D, and with that probably next Tuesday we will complete the course because Thursday is a holiday, and then the week after that you will start your exams. So we have only 2 more classes left, this Thursday and next Tuesday. This Thursday we will look at 2D and we will start 3D, and we'll probably complete that 3D aspect in the next Tuesday class as our understanding of the important aspects of 3D elasticity to take forward. So now the class is formally ended, but any of you who are willing to stay back and ask questions, I'd be most happy to answer. Okay, so if there are no questions, think about it. Next class also you can think of any questions that you might have based on, you can look at the video as well, and then come back and let me know if you have any doubts or questions, and I'll try to clarify that. Thank you very much. Bye-bye.
Thank you, sir.
Welcome.
Thank you, sir.
Most welcome.
Thank you, sir.
Welcome, Krish Kumar.
Thank you, sir.
मृत्युंजय मंत्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा